and I record the lecture, obviously, I'm going to move in the class between Canvas and my Notability, where I will use this to write. So you see it easier as opposed to writing on the board, because writing on the board is not very clear, right? We discussed that. Okay, so in case you have any difficulties seeing what I'm doing, let me know, because today I'm gonna try this using two, one iPad, one laptop. So just to summarize, we spent last week 2 lectures trying to introduce our way to electromagnetics, right? Electric and magnetic fields. And we try to explain why those are important. And we try to connect what we do with the rest of what nature has, all right? The rest of physics. And we try to explain why those are very important fields and how do we derive the concept of the field from the forces that we feel in nature. Since we have a mass, we feel those forces, right? We do not feel the field because the field does not exist. We make it up. It's like a mathematical construct that we are using. So we can manipulate those forces. Otherwise, we will not be able to do that. Okay. Also, I mentioned that there are specific things that we would need to review from our previous classes that have to do rather with math. So the definition of vectors, vector properties, and so forth. I'm not going to spend time as I used to do in the past, all right, trying to do that review and then start with electrostatics. The idea here is to start with electrostatics and then along the way explain why we need the other entities, all right? And then we are going to therefore try to integrate the two as opposed to doing math and then going to electrostatics. I did not think in the past that really helped anyone. It just was time because we had to revisit them anyways, those concepts. So today what I wanted to do, I will start with this. And I believe everyone sees that. This is my own writing. So I want to thank someone who read this and corrected an error that I made. So you will see that because I'm going to correct it here. What we discussed last time, all right, from electromagnetic, the electromagnetic force, we went to fields, but you're going to see here that progression too. But now we are going to use some math also, all right, in the process, because it's not just, it's one thing to talk about those phenomena, the forces that we've seen, but we have to use that information. And we are engineers, all right? It's not just how something works, but what it is, but how we can use it to do something with it. This is the most important question we ask in engineering. All right, so we also mentioned that the electromagnetic force expresses itself in 3 separate ways that sometimes to us are explained as being different, but they are not, all right? So one is the electrostatic force, the other is the magnetostatic force, and the other is the electromagnetic. And here what I will do as and also here what you see is what I mentioned last time. Electrostatic force is what is produced by a static charge, and then I will show you some pictures here to keep them in mind. Magnetostatic force is what is produced by a moving charge with a charge that is moving with a constant velocity. Electromagnetic force is produced by a charge that is moving with a variable velocity, all right? So a velocity that changes either in direction but has the same value, or it changes both in value and direction. So that is, all right. So a force that somehow has, demonstrates that there is some kind of a form of acceleration somewhere. All right, so now I will add one page here because I would like to write on this and show you visually. There was a question I got from one of your colleagues that it had to do with the magnetostatic force, and I thought it's important for all of us to be able for all of us to see exactly the explanation that I gave to him. So the first one we said, and in fact, for a moment, wait a second, so I get all of my tools here. Right. Let's assume that we have one static charge. What is one static? How does it look? I mean, if I were to write it myself, and you will see me doing this below, it's going to be like a charge. And then here, of course, I have to write positive or negative. And that is important, all right? Because you will see how we will display the direction of the electrostatic field. We said that a charge like this Q that stays stationary, it's in one place, has one value. It creates a force to any other charge that enters into its vicinity. If the other charge, and then let's assume that this charge is somewhere here and is negative. If this other charge, this is Q1 and this is Q2, is very close, that force is going to be strong. And if it is very far away, the force is going to be very weak. The bottom line is that this force always exists, even if this charge goes to infinity, which means that if you go to infinity, infinity can be, for example, depends how big the charge is, all right? But the infinity can be like in another building, in another room, it can be like in another town. The force is going to always be there, but it's going to be very small as you move away, and we will see how it varies with distance. But for these two, we know that the electrostatic force, you will see it below, the electrostatic force for this is Q1 times Q2 divided by 4 pi epsilon naught d. This is the distance, d. I will put d here, even if later, and I will write it as a scalar, even if later you will see that definitely it has a direction. But there is one point I want to make. From there, we are going to go to the electrostatic field. And you remember we said before, and I will rewrite it, and you will see it again later, that the electrostatic field, in this particular case, is F sub B of the electrostatic field that is due to charge Q1. So I will write here Q1. I will not always write those things, all right, so explicitly, because then the symbols become very complex. But for now, is this divided by Q2? So practically, the electric field due to charge 1, see, I don't have any vectors anywhere, so only scalars for now, is Q1 divided by 4 pi epsilon naught, and at distance d. What does that really mean? I don't have a Q2 now. It means that this one, let me in fact highlight it. This one means that if I remove charge Q2 for a second, I remove it. And then I keep still distance d, so practically I put this point here. That tells me that if I have one charge Q1, then that creates an electric field, all right? So from a charge Q1 creates an electric field EQ1, which then, if another charge Q2 comes to the picture, and then, so let me, I don't wanna, this is bad symbolism here. If another charge comes into the picture here, that means that the electric field that has been generated by Q1 is going to exert a force on Q2, which means now that I'm having this force E, which is exactly what we had above. So there are two ways to talk about fields and forces, all right? Either you start with the concept of the force, two charges feel a force, or you start with the concept of an electric field, one charge creates an electric field, and then when you bring another charge, feels the force. All right, so these are two ways. One important thing, which in fact, you will never see me writing those again without a vector identification to these quantities. Why? Because forces have directions, and therefore electric fields have directions. And now we go to the following. And let's, in fact, go with this approach here, starting with electric fields and then talking about forces, because that is what we are going to use from this point on. All right. So even if forces is what we have observed, the first thing that we observed was a force. However, in everything we're going to do right now, we are going to start with the electric field. All right. So it is this progression in red that we're going to follow. A charge creates an electric field, which creates a force on another charge if it comes into its vicinity. All right. So, and in fact, as you see moving forward, we are going to even stop talking about forces, because in reality, we don't have to measure forces. We have the capacity to measure fields. And then we'll talk about this next. But in reality, even if this is what we mean, many times you're gonna somehow do not necessarily have the last piece here may never really, I mean, we will imply it, but we'll never say it explicitly. Okay, so we will always stop in the following statement. A charge creates an electric field. All right, that's the statement. Now, how do we go to these scalar entities and we place direction on them? We make them vectors because there are directions involved in forces. We said that if, before last time, and here also, that if this second charge that comes here is a negative charge, okay, Q2, then this is an attractive force. Attract these to the other charge, Q1 to Q2 and Q2 to Q1. And in particular case, which one is going to move, if we were allowing the charges to move, would be the smallest going to collapse on the largest, all right? Because the field of the largest charge is the strongest. So yes, that's what would eventually happen, but it doesn't. In any case, but I mean, theoretically speaking, if that were possible. From physics, that is not exactly happening. Charges like that do not collapse. They do not collapse in solid state electronics, as a matter of fact. You will see the collapsing in a different way. And why do charges do not collapse, positive and negative? Because there are no negative charges. What the negative charge means is the lack of a positive, what a positive charge means, excuse me, they are not positive charges. What a positive charge means is the lack of a negative. So in physics, in nature, in the place where we live, which are the only entities that have been recognized as carrying a negative charge? The electrons. These exist, all right? We said last time protons are positive charges. But what does that mean? That the neutron before had electron, had whatever, was neutral. That's what it meant. The moment you create an electron that was created, is a real thing, it exists in nature, and was negative, the rest that was left behind was positive. But electrons and protons do not collapse because of all of the other forces that apply on them, and they keep them in a balance, all right? So charges never collapse. So you said, okay, if charges never collapse like that, why did you tell me that in solid states you have positive and negative charges that come? and neutralize, because in our macroscopic world, all right, in macroscopic world where we are engineers work, at least to make the kinds of circuits, unless you are a solid state electronics person. In the macroscopic world, there are only negative charges, electrons that move. And then what is a positive charge? The lack of an electron. Usually all of our masses are neutral. I don't have a charge as a person. There are a lot of molecules and ions in my body, and of course many atoms, and they have electrons, and then there is a whole combination of a lot of different negative charges. But the whole thing is neutral, which means when the electrons are sitting separately, the other places that seem to be positively charged, it means that they have missed an electron, all right? If somehow all of the electrons were, if all of the forces were to collapse for some reason, all right, tomorrow, all right? So there are no forces that apply on anything microscopically, that all of the electrons will go into the nucleus practically. I mean, they will collapse on the protons, and then the whole thing will become neutral, all right? So we are going to stop existing, but it does not matter. The other thing is that it will all become neutral. So when I say there is a negative charge Q2, I mean an electron or many electrons together. Now we are macroscopically, of course, you cannot physically think of the electrons being sitting one on top of another. Usually they go around like the planets around the sun. However, you know, macroscopically, yeah, we can collect them, all of them, say we have negative charge. The positive charge means that I have removed electrons. How do we remove electrons from a conductor? By grounding them. You will see that later. So physically, all of these things can happen, all right? However, we're not going to go into the details how I create a positive charge, how I create a negative charge. I'm not going to go into these details. So we are going to use some we are going to agree on some things that we are going to use, knowing what that means. Whenever we talk about an electric field, like Q1 is going to always be positive. So when we say I have a charge Q1 and I have an electric field, the condition, unless I want to change it and I have to explain it, all right, I have to state it. If I don't state anything, but I say I have Q1, that implies positive. And if it implies, this is like a condition we've made, all right, an agreement we've made. And if it's positive, that in that case, we will also assume that another charge that might be away at infinity, I don't show it anymore, if it's gonna be also positive, which it's gonna be, excuse me, another charge at infinity, we may not necessarily know, we are agnostic about what it is. And the agreement is that if I only keep the positive charge here, all right, and I want to talk about the electric field that is excited about this from this charge, then this electric field, of course, is going to be a vector, because eventually it has to give rise to a force. The force exists, the field is some construct, and always the direction from a positive charge of the field that a positive charge creates is going to be outwards. Okay, always. So now, if we make this assumption, this one becomes a vector, all right? E here becomes a vector, and therefore I have F becomes a vector, but I have in that case to put a vector next to this quantity. And this vector, we normally show it like this. Okay, so this is I have summarized a theory that you have seen before, all right? We start with one positive charge. We define the field from this positive charge. We assume, I did not say Q1, what it was, we assumed positive. The field is gonna be outwards from the charge, and the field is gonna be given by this one then, all right, where this is the direction of the field, and it's a unit vector, a radial unit vector. So you see, we are introducing one step at a time things that we have to remember from the past. But I'd rather do it while we're introducing also the physics concepts here and not on their own. Okay, so practically a lot of times you're gonna see written in many books that here you have, as part of a problem, a positive charge, and this generates a field like this. All right, so the field then from a positive charge is a vector. Now, what happens if we have a charge that moves with a constant velocity? What are the cases where we have a magnetic field, and why do we have two magnetic poles? That was the discussion, all right? A magnet has one positive, one negative pole. Why? I mean, but we don't have magnetic charges. Magnetic charges do not exist like electric charges. So what is it that makes the magnetic charge an equivalent entity? When we say equivalent, physically it does not exist, but we just make it up, all right? So, for example, an iron magnet, how does it work? Can anybody tell me? Since we don't have charges, let me add here a page. Since we don't have charges, why sometimes we show a magnet like this, and then we show positive here, negative there, and then we show something like that? That's also how the magnetic pole, the magnetic field of Earth is, North Pole, South Pole. So what happens? We said previously that a magnetic field is generated out of a charge moving with a constant velocity, okay? Now, if a charge moves with a constant velocity in a small circle, so the question is, what are those here? So magnetic poles, plus A and minus. All right, if a charge moves in a constant velocity like this, but moves around on this circle forever, all right, what does it create? A small loop of a current, all right? The small loop of a current creates what kind of a magnetic field? Like this, as we will see later. What does that mean? That if I have two loops, one like this and the other like that, so here is Q1, here is Q2, B1, B2. That means that these two charges that run like this on these small loops, they will feel a force, which is the magnetic force. But instead of a charge looping, I call that what? An infinitesimally small current. And this is what creates the magnetic field. So the equivalent to an electric charge, an infinitesimally small electric charge, is an infinitesimally small electric loop. And that exists because it's a charge that's moving like that. Now, how do they exist in nature? In nature, we have inside materials, depending on the material, you have small ions, meaning there may be molecules of the material where all of the electrons for all of the chemistry and the mechanics have moved to one side, and then of course there is a lack of electrons on the other side because every molecule is zero. But the electrons can move on one side, all right, because of all of the dynamics of the forces and because of the chemistry. All right. And also because of the same kind of forces that apply in the material, that what we call dipole, because all of the electrons have moved up and all of there is a lack of electrons on the other side is positive if it's negative on one, then those electrons move like this, all right? They move around a loop. That's what happens in iron. So practically you have these loops there, which look like magnetic charges, all right? So remember that physically exists. So we have therefore a magnetic force, and then we have the electromagnetic force, which happens like an antenna. Do you remember the all? Have you seen on pictures? Don't remember because they were before your when you were born. But on pictures you may have seen these dipoles. Then the old phones. You remember they had an extension. That was a monopole, we called it. Like in reality, a dipole. It was over ground, so it looked like it acted like a dipole. All right. That was the dipole is nothing else but a piece of wire that is fed at the center, and then if it's fed by an RF current or an RF voltage, has electron, negative or positive charges, but they alternate. And those alternate with the frequency of the coming wave. And when they alternate, what happens when a charge runs from one end to the other and then it has to turn and come back? It has to decelerate and accelerate, all right? So it forces the charges to change their direction and their velocity. So there is acceleration and deceleration, and that creates an electric and a magnetic field. They create two fields which are interrelated, and they are coupled strongly, and that is the electromagnetic, all right? So these are the three different forces we see. So here is the mistake that I've done, which I have to correct. So it says pushing the two charges away. Away from. I will correct it on my all right, so we talked about this, all right? So opposite polarity charges attract. Of course, there is same polarity repulse. This is your electrostatic, all right, force. It's here. Electrostatic force. And from the electrostatic, one thing that you need to pay attention, because now we are going to get into some more details. Look at how I have written the electrostatic force. Okay, and here it is exactly how carefully we are going to write it. We have, if we have two charges, we have, of course, to designate the center. The charges can be distributed over a volume, all right? Or they can be one charge, but we show them like this. We connect one charge to the other, and that distance we consider it to be a vector, because it's not just the length of the distance or the distance between the two charges, but also to that we assign the direction of the electric field. So if our original source is Q1 and the other is a charge that found itself in the vicinity of Q1, then we assign a unit vector to this distance, which I call R. So I use all of the same symbols with the book, all right? So that's part 2 of the book that we are entering. Part 1 is gonna be for review. We are gonna review it all along. So this one now, it shows us that the distance is a vector. It has a value R, which is the length of the vector. It has the direction. And we show the direction by this unit vector. and see how we're gonna see that later, but I wanna remind you that in this one here, this is how mathematically we'll define the unit vector. Is the vector R divided by its magnitude. All right, so if you have any vector, and you want to define its unit vector for that particular vector, you take the vector, however you express it in Cartesian, cylindrical, or spherical coordinates, and then you divide it by its magnitude. All right, and that is going to give you the unit vector. So this is the correct mathematical expression that we are going to use. And of course, in electrostatics, that's the field. Now the field is a vector, has the direction assigned to it, which is given by this unit vector. All right, and if you want to show that, here is how you show the field around it. Okay, and as you can see, is a function of the magnitude of R. It goes as the distance square. All right, goes as a distance square. Why is that? Because if you think of as power, you have an antenna that can send out 5 watts. And these 5 watts are going to go out in the form of an electric field. But the 5 watts who are at one point here, they are going to distribute over a whole volume. So it goes down very fast, the power, okay? So the electric field is 1 over R squared for a point charge. It changes for other types of sources. It will be a different type of a change as a function of the distance away from the source. All right, so this is our introduction to fields and electrostatics. But the one thing then you have to see here is that we cannot go any further than this unless we remember some things about vectors and about properties of vectors and about coordinate systems. And why is that? Why can we not go any further than this? Because, okay, you found, for example, the electric field from one charge, static charge. What if we have 2 charges? And I'm asking you to find the total electric field from the 2 charges. Every charge is going to create its own field. And then you will have to know how to not only describe each one of the electric fields as a vector, but how to sum them up. So for example, one is to ask you the following problem. And this is not like a theoretical problem. Let's assume that I have 2 transmitters in this class. I'm doing a radio experiment. I have 2 radios, all right? This is my radio. You have your own radio. And we have receivers. And we would like to find out where is the best place to place a receiver for maximum reception. How are you going to do that? You have to assume that a transmitter, very simply, for example, let's assume that one transmitter is here, point A. Another transmitter is point B. All right? Let's assume that the transmitter sends all around, which is not necessarily true, but we are going to assume that. It's like a charge everywhere, the same power. It's called it's a uniform in space distribution of the electric field, all right? For simplicity. Let's assume that one charge, it's one type of a transmitter that I see here. And usually, let's assume that they are static transmitters, not the ones we have in radio, which are electromagnetic and they have frequency, all right? Eventually, the same kind of thinking applies there, but gets a little more complex because you have signals that change with time. But now let's assume that it's statics. So you can see, you have 2 charges. One charge generates, let's assume that one is a positive charge, Q1, positive, and then the other is Q2 negative. all right? And I want now to find out where I'm gonna place a receiver for this static, something that can receive the maximum. So to be able to find where is the maximum between the two, where is the maximum field, I need to find out each one of those fields and then sum them up. Don't you agree? So one field, for example, the purple one, let me do the another color, it's going to be Q2. The purple one is going to go like this. And it's going to be, all right, so it's going to be like this in this direction. Okay, always like that. And the other one is going to go, the Q2 is going to go like this with what we know so far to see what else we need to add to our toolbox to be able to solve this practical problem. So the other goes like that. And the field goes like this. Okay. So practically, if I remove all of these that now I've done, just to simplify things, and I look at one point in place, and let's assume in space, and let's assume that it's this point that I'm looking at. What happens in this particular case? Then at that point in space where I'm going to find the total field, I know that I have one field from Q1 going like this, sorry. All right, and this is E1 at this point. And the other goes like this. Because it's negative, it's going to go into this direction. And it's going to be E2. So you have it at this point, P, for example, which is an observer, or O, if you want to call it observer, this point. I have two fields, one like this and the other like that. What is the total? I have to sum the two vectors, all right, to be able to find it. And then that's simple because it's a very simple problem. If you go to more complex problems where the sources Q1 and Q2 are different, then I will have to do a lot more things to be able to calculate a problem like that. Now you can say, okay, where am I going to have an issue like that? There are a lot of applications, for example, in statics, especially in digital circuit, when you do digital circuit design. And then when we are going to get to that point, I'm going to show you examples where these fundamental things become important just to find very practical rules on how close to put two lines, because in digital lines send steady currents, all right? They don't have high frequencies. So you can assume just charges, all right? You can assume practically when you have two lines going like that, that you have some kind of static charges, and you want to find what kind of fields you have around and how strong the fields are. And if one line, if you put it next to the other, is going to see it. Because if the two lines, electrically speaking, what does it mean that electrically I see you? It means that you have a strong enough electric field that I sense it. I sense the force. That's what it means. I see you electrically, all right? So if two lines can see each other electrically, you know what that means? That means that they will couple. That means that it's going to be transfer of information from one line to another. You don't want to have transfer of information from one line to another when the two lines have separate signals that they transmit, because then you create a lot of noise in your original signal that you want to process, all right? So important, simple things like that become very important. Now, however, I'm going to stop here and say that the only way we can find out more, solve this problem, is if we go to vectors. And now, I'm gonna take you to this. I think we are gonna, I have left spaces just in case somebody has a question to write in between. But let me talk a little bit about, since we're talking about vectors, is the second in line. Usually the quantities we are using to understand nature are 4 types. Scalar, we use numbers without directions. Could you tell me an example where that is what we are doing from real life?
Cars, speed gauge, cars.
Okay, or temperature. Okay, when I say, you know, I feel like hot, probably around me, it's like 72, 75 degrees, I don't know. So other things, as you said, I mean, there are many other cases where we want the number, but not necessarily the direction, scalar numbers. Vectors, obviously, when the direction is important, like forces, electric fields, all right, velocity, acceleration, all right, so matrix. Matrices are used if, for example, you have a house with 4 rooms. You will see it somewhere in my notes. And you have only 2 thermostats. Now that's not a very good control because, as you know, in big buildings, the worst problem is to control temperature from a number of thermostats, and you cannot control every room separately because you don't have this much space and for this much equipment, all right? So what do people do normally? They characterize, they do a number of measurements. If you want to know exactly how to put the thermostats, so you know what kind of temperature you can get in every room. So you do different combinations. The experiment is you create 20 different combinations of the temperature in the thermostats in the range of interest to you. And then you go to every room and measure the temperature. So if for each one of these 20 combinations, you have 4 measurements. The one way to put this together is in a matrix form. You put this together in a matrix form, and then you create a small little program that whenever you push one T1 temperature in one thermostat, T2 temperature in the other thermostat, it gets you know exactly what the temperature in the rooms is going to be. All right. So it's like something like this to get an understanding where a matrix can help. All right. Tensors are a little more difficult. I don't know whether you've seen them, but a tensor is a vector, is like a vector where each of the components of the vector are different vectors. So you may say, where do I need those? Okay, scalar, you know, these are scalar quantities, vector quantities. I said that will go another vector, right? This shows how Earth goes around the sun. Matrices, I just said that example. And then tensors. If you have this problem where you are in microscopic world, and you have then you have clusters of charges together, or you have like a big one that you see here, you have a cluster of different particles which are charged, and therefore they are connected, and then you have individual particles, and then all of a sudden another particle hits, for example, the cluster and push away different particles. When you have a particle, you have a cluster that moves in one direction, and then you have a particle that hits it, and then there are particles out of the cluster that move away. To be able to characterize that problem, you will need to have the capability to use this tensor, which is something like that. We are not going to use this in class. It's mostly something you see when you have very unique materials, or whether you have microscopic kind of phenomena. For us, for this class, we are not going to use tensors. But if case you see something with 2 bars, that implies it's a tensor. Okay, so with the introduction, the last thing I wanted to do for you and have you review is vector properties. We talked a little bit about summation, all right? And what I want you to see here is how we did that in a simple Cartesian coordinate system, all right? Every vector has 3 coordinates. And then how you write the different AB, the difference or the sum of the vectors in the same Cartesian coordinate system. You remember we talked about this as being the sum, and then in fact the difference, last time I said I flip this over and I take the difference between these two. So in fact, well, let's see, I take the difference between these two. So in fact, I will find exactly the same, just the way I have done it. If you don't want to flip over things, as we discussed last time, this one that starts from the common point of the 2 vectors, one diagonal is the sum, the other diagonal that goes from the negative vector in this particular case to this one. To the positive, its diagonal is the difference. This is the difference, B minus A. Okay? So this one I want you to review as properties. Next time, I'm going to, I want you to read a little bit ahead because you have seen that we are going to talk about the product of 2 vectors, and there are different types of products of 2 vectors. And this is the unit vector we discussed, but now next time, I'm going to briefly, I want you to review it because you have seen that. This is exactly how you write a vector, and this is how you find the magnitude of the vector. This is how you find the unit vector that characterizes the direction of the original vector A. All right? Remember, you have seen this before. And here it's just a summary of the properties. So you have all of the properties here. You have seen this before, is that right? This is a review. On the basis of that review, I will open today an exercise. And this exercise, you will have to do it until Wednesday morning, before the class, okay? It's based on these kinds of properties. So that's all for today, and I will see you on Wednesday, yes.
Since the exercises?
Exercise. All of these exercises are individual. They are not team exercises there. Yes, yes. Thank you. Bye-bye, goodbye. Good morning, how are you? I was busy. How about yours? It's so busy. Oh my God, I mean, it's, anyway, but that's okay. That's what we've chosen to do.
Yeah, exactly.
If you love what you do, you can keep going, as they say. That's the good thing about our profession, you know. It's not like a job.
No.
It's like a lifestyle. Let me tell you.
That's what I
Not going to be